Section 5.2 covers random variables. When we talk about a random variable, we're talking about a variable that is a single numerical value which is determined by chance for each outcome of a procedure. Think rolling a die, which has 6 potential different outcomes, though only one of them can occur at any given time. A probability distribution lays out all the different outcomes that a random event can have along with their associated probabilities. Oftentimes we'll see it expressed as a table. So take this example. Consider flipping a fair coin 5 times and counting the number of heads. If P heads, or the probability of getting heads, equals 50%, we will let the random variable X represent the number of heads obtained in 5 flips. X is a random variable. Since we don't know how many heads we will get, we can get anywhere from 0 heads to 5 heads when we flip this coin 5 times. Now it's giving us the probability. It tells us that this is a fair coin, meaning the probability of getting heads is 50%, tails is also 50%, and based on that, we could fill out a probability distribution, okay, which is a table like this. It has all the different outcomes, okay, of 0 heads, 1 head, all the way up to 5 heads, along with their associated probabilities. Okay, for example, there's a 31.25% chance that we'll get 3 heads when we flip a coin 5 times. There are 2 types of random variables, and we've talked about these terms before. The first is a discrete random variable. These are countable values, such as the number of eggs that a hen can lay. A hen can't lay 2.35 eggs in a day. The other is the continuous random variable. This takes on an infinite number of values in a continuous range, such as the amount of milk that a cow produces in a day. He might produce 1 gallon, 2 gallons, or anywhere in between that. Most of the time, we're going to see our information presented in a table like it was 2 slides ago, but sometimes they'll give it to us in a probability histogram like this right here. So probability histograms are just like our old histograms, with the only difference being that the sum of all our bars total 100%. Okay? In any probability problem, the probabilities have to add up to 1 or 100%. Also, each individual probability needs to be between 0 and 1. First example, is this table shown here a valid probability distribution? So we want to make sure that those 2 rules on the previous slide are met. First off, taking a look, all of these probabilities are in between 0 and 1. So they all look like valid probabilities. The other thing we want to check is, do all these numbers add up to 100%? Okay, if we add all these up, they total 0.91. Okay, that's no good. This is not a valid probability distribution. There are 2 exceptions. Okay, if we added these up and they totaled 0.99, that's okay. If they totaled 1.01, that's okay because of rounding issues. So if we're rounding our data, it's okay to be whatever decimal place our data is off. If we're 2 decimal places off, 0.98, no good. 1.02, no good. In example 2, 76% of adults in a certain town have health insurance. We're randomly selecting 2 adults from this town and then counting the number in those 2 that have insurance. Before we do anything else, let's fill out the top of this table here. If we're picking 2 people, either 0, 1, or 2 of them will end up having insurance. Also, if 76% of adults have insurance, that means the other 24% don't have insurance. All that said, for us to end up with this situation right here, we've picked 2 people that have no insurance. This is a compound event like we did in the last chapter, 24% for the first and the second. Multiply them to get the probability of that event occurring, 0.0576. Okay, let's jump over to this one since this is the next easiest. 2 people that have insurance, 0.76 times 0.76 gives us this probability. The one in the middle one is the hard one because we can pick someone who doesn't have insurance followed by someone who does, or we could do it in the opposite order. Pick the person who has insurance first and then someone who doesn't have it. Okay, it's an or problem. We do each of those, we add them together to get this final probability. Note that all these probabilities have to add to 1. It's a probability distribution, which means really once we find these 2, we don't have to go through the math to get this middle one. We can just subtract the sum of these 2 outside ones from 100%, from 1. Some of these things are going to look familiar from earlier chapters. Range rule of thumb allows us to identify unusual values. Anything outside of 2 standard deviations from the mean is unusual. So we can find the minimum and maximum usual values by just taking the mean and adding or subtracting 2 standard deviations. There's a similar rule for probabilities. Anything that has a probability of 5% or less is considered unusual. These are our equations for the chapter. You'll get an equation sheet with these for the quiz and test. Mean, variance, and standard deviation are all here. 2 things to note. If it asks for the expected value, that's the same thing as the mean. Those terms are interchangeable. And standard deviation is just the square root of the variance. In example 3, we're flipping a fair coin 10 times, counting the number of heads. If we do that, we would get a mean of 5 and a standard deviation of 1.581. Based on those results, is it unusual to flip 8 heads in 10 coin flips? So we want to use the range rule of thumb, find a minimum and maximum usual value. Minimum usual value, take the mean, subtract 2 times the standard deviation. Anything below 1.838 is unusual. Same thing for maximum, except we're adding anything above 8.162. All right, that being said, we can see that 8 is just within 2 standard deviations from the mean, so we wouldn't consider it unusual based on this rule. And lastly, number 4, here we have a table that shows the probability distribution for the number of peas with green pods from 5 offspring peas. This is from Mendel's famous pea experiment. We want to find the mean, variance, and standard deviation from this table. Now, just so I don't confuse you as I change the direction of the table, I wanted to make sure it fit on the slide, so I took all this and I just changed it to a horizontal display. All right, we want to find the mean. To do that, we're going to fill in some additional rows. We want to start by doing x times p of x. X times p of x is just each column, take x, multiply it by its probability. Okay, we're also going to find out x squared times p of x. I'll do it from this side. So in this case, we would do 5 squared times its probability. 4 squared times its probability. Okay, those are going to go in this last one. We do that for every column. Part A, find the mean. Equation for mean is just x times p of x. This is the same as the expected value. We're taking this whole column, adding it all up, and we get 3.752. Part B, find the variance. This is a more complicated equation. So we're taking the sum of x times p of x. Okay, so now we're talking about this bottom one. Add those all up, and we're going to subtract the mean squared. So 15.004 is the sum of that whole bottom column minus the mean, which we got up here, squared. That gives us a variance of 0.9265. Standard deviation is just the square root of the variance. So we're taking that variance of 0.9265, square root it, and we get a really similar 0.9625. Lastly, based on the probabilities in the table, is 1 an unusually low number of peas with green pods. So the probability of getting exactly 1 pea is 0.15. Since it's talking about it being low, we also want to include everything beneath it, because if 1 is unusually low, anything below it would also be unusual. So we really just take everything below it and we combine it. So we add in that 0.01 to get the probability that we're going to compare to 5%. Okay, so 0.15 plus 0.01 is 0.016. It's unusually low because that's below 5%.